Welcome to iLecture Online, and here's another example of how we're going to find the moment of inertia of an oddly shaped object. In this case, it's a solid cylinder, length L, mass m, and radius r. So how do we find the moment of inertia? And notice that it's rotating about a central axis that runs through the length of the cylinder. All right, again, what we're going to do is we're going to assume a small little segment of this cylinder, like so. Let me kind of get rid of that little arrow and put the R a little bit different so we can have this as a cleaner example. So let's put the R over there, and let's say we have a small little segment of the cylinder along a small little thin shell somewhere in the middle of that cylinder. And let's call the distance from there to there, let's call that x. And let's call the thickness of the little shell dx. And of course, that little shell then will have a small amount of mass called dm. Now, let's also assume for a moment that the cylinder has density rho, and by definition, the density of that material is going to be equal to the mass over the volume. Okay? Now, and I guess I want to use big M because I use big M over there. So let's use big M over there. All right, so how do we do that? Where do we go from here? Well, I'm going to find the moment of inertia of that thin little shell. And of course, that thin little shell goes all the way through the cylinder, like so, all the way through the cylinder, like so. So imagine we have this thin little shell running all the way through the length of the cylinder. What is the moment of inertia of it? So we can say, well, that's going to be di. And so the moment of inertia by definition is going to be the mass of that little shell, which is dm, times the distance away from the center rotation, which is going to be x squared. And of course, then if we want to find the moment of inertia of the entire cylinder, we're going to subdivide this into a whole bunch of little shells, an infinite number of them, and add them all up. So that means that the I is then going to be the integral of all the di's, which is going to be the integral of all the dm's times x squared. And the limit of integration is going to be from x equals 0 to x equals the radius of the cylinder. So x equals 0 to the x equals the radius of the cylinder. All right, so now we could integrate that if m of the dm is equal to x, the variable inside my integral sign, which of course it isn't. I have to somehow convert dm into something in terms of x. So let's see now. What could we do? Well, the dm is going to be equal to the density times the dv. Let's see if that's correct, because by definition, density is mass over volume, so therefore mass is equal to density times volume. So the dm could be expressed in terms of the density times the dv. I think I'm onto something now, because what is the dv of that little line segment? Well, if I cut it with a scissor and I lay it flat, then what is the volume of this thing? That would be like this. That would now be kind of a thin strip like this. So the circumference of this circle, which is 2 pi x, would now be this distance right here. So this would be 2 pi x. That would be the circumference of the circle when I lay it flat. The thickness would be dx, and the length of this would be the length of the cylinder, which is L. And so I can say now that the dv of this, which is the little segment that I have in here, is equal to the width times the length times the height, which is 2 pi xl dx. So that's my dv. And so my dm can now be replaced by my rho, my density, times the dv, which is this. So this can now be written as the integral from x equals 0 to x equals r. And instead of dm, I'm going to write rho dv. So I'm going to write rho, the density, and I'll worry about the density later, times the dv, which is 2 pi xl dx, times, of course, my x squared, which is still there. All right, so of that amount that's inside the integral sign, what is the constant? Well, definitely the density is a constant. Well, we can make it more complicated by making density a factor of length or so forth, but we're not doing that. That's a constant. 2 pi is a constant. L is a constant. All that can come out of the integral sign. So this is going to be equal to 2 pi L times rho. So 2 pi L times rho out of the integral sign times the integral of x equals 0 to x equals L. And what's left? We have an x here, we have an x squared there, and have a dx. So that becomes x cubed dx. All right. So now that we know how to integrate, because the integral of x cubed dx is simply x to the fourth over 4. So this becomes equal to the 2 pi L times the density times x to the fourth over 4, and we're going to evaluate that from x equals 0 to x equals L. Did I say L? No, I don't want L. I'm integrating from 0 to r, not to L. I don't want the length. This has to be r. So from x equals r to x equals r, like that. That's better. I'm integrating along the radius, not along the length of the cylinder. Okay, so when I plug in the limits, when I plug in the upper limit, this becomes r to the fourth. When I plug in the lower limit, I get 0, so I don't have to worry about the lower limit. So this is equal to, and I can bring the 4 out. So this is 2 pi L rho times r to the fourth over 4. And then notice that the 2 and the 4 can cancel. This becomes 1, this becomes 2. So this can be written as 1/2 pi L rho times r to the fourth. All right. Okay, continuing now, we want to come over here. We have a little bit more room. We now want to express this, of course, in terms of mass and the radius, and we don't have a mass in there. So coming back over here, we know that the definition of the density is the mass over the volume, and the mass of the cylinder is m, and the volume of the cylinder is the area of the base, which is pi r squared times the height, in this case the length, is L. So we can replace the density rho by m over pi r squared L. So by doing that in here, so this quantity right here is now going to be replaced by this. We get, this is equal to 1/2 times pi times L. And instead of the density, we're going to write m over pi r squared, oh, that's a terrible looking 2, r squared L times r to the fourth. All right, now we can go ahead and simplify some things. We can get rid of pi. We can get rid of L, and so this now becomes, oh, and we have an r squared here, we have an r to the fourth, so this cancels out with 2 of those, and this now becomes 1/2. We have remaining an m, and we have remaining an r squared. And that indeed is the moment of inertia of a solid cylinder. Now notice, one variable is missing, or one aspect of the cylinder is missing. The length is missing. It really doesn't matter how long the cylinder is. A short cylinder or long cylinder makes no difference. The only things that determine the moment of inertia of a cylinder rotating about its axis, its central axis, is the mass of the cylinder and the radius of the cylinder, and everything else doesn't matter. Okay, so we have just shown now how we find the moment of inertia of a solid cylinder. And in the very same way, you can find the moment of inertia of any object. So we'll leave it at that. Now the next videos are going to actually show you some applications of how to use the moment of inertia in various applications, such as the kinetic energy of rotating objects, finding the moment of inertia of all kinds of different objects, actually the numerical values thereof. So let's stay tuned and see what we have in store for you.